אוקיי, שלום לכולם. אז היום אנחנו נתחיל לדבר קצת על אלקטרוסטטיקה. שמעתם עליו בעבר, אז אני אתחיל בסוג של כזה. No, I speak English. Sorry about it, I don't know Chinese, so I'll speak in English. So at least you'll learn some English in this class, that's already good. Okay, so we are going to discuss today electrostatics. And this is something that at least at the beginning I think you heard about, but we'll have a rehearsal in some sense at the beginning. And we will introduce the notations that we will use all along the course. I am following in this course the book of Griffiths. So I think it starts slow and then it goes up exponentially. So let us start. So electrostatics. What is electrostatics? I have charges that are fixed in space. I take a nail, I have a charge, I nail it to the wall and it does not move. That means it is static, it's not moving. If it's not moving, it means there are no currents in the problem. If it's not moving, it means there are no magnetic fields in the problem, because what creates magnetic fields are currents. So we are dealing essentially only with electric fields. That's it. And that's why it's called electrostatics. There are, of course, magnetic fields which are statics. Now, there are two ways that we can describe this phenomena. One of them is based on Maxwell. Where is the line? This is the line?
The red one.
This one? Oh yeah, here, this one. Oh, this is horrible. Okay, so we have electrostatics. And we have Maxwell, who tells us, I think it's with double L, check with ChatGPT, who tells us the following. First of all, the rotor, the curl of E. So first of all, we are caring about the electric field, so we want to calculate the vector field E in space. So this is a function of R, of the vector R in general. This is equal dB dt, but as I mentioned, nothing is changing in time. This is equal 0. So the two laws are essentially very well known. We have this law, curl E is equal 0. And the second law is Gauss' law, which is rho of E divided by E0. So these are the two laws. And essentially, this is all of electrostatics. You need to give me rho, which is the density. Give me the density, and I'll find you the E. Or you can think about it a little differently. Maybe give me the density and then find E, which is the same thing. Usual problems are, I'm going to give you the density and you find me the electric field. But actually, if you're an engineer, and you want to design some E, you want to know what is your density to get it. So it can go both ways, and we will talk about this a bit more. So this is Gauss. The Gauss law is also formulated as an integration. We'll see that later. And that is. Actually, the interesting question is, what is this density? So this charge density has units of charge divided by meter to the power 3. That's the usual density in 3 dimensions. But what is the density? So the density, you can look at it in two ways, and this will be some theme in this class today. I'm going to look at it in discrete way. So what is the density for discrete charge distributions? So what are discrete charge distributions? Discrete charges, I mean point charges that are zero size, that they stick in space somewhere. So in discrete world, these are some reference frame, and I have some charge Q1 here, Q2 here, etc. That describes a density. What is the density in this case? It is, yes, it is, the density is Qi sum R minus Ri, and you need to sum I going from 1 till n to the number of particles. And this is a discrete density. You can think about it, the microscopical density of objects which have zero size. In reality, this density you can treat if you have, let's say, 2 or 3 charges or 1 charge. The most famous case is the Coulomb law. But in practice, what we usually deal with, we deal with something totally different, which is the continuum. So continuum description is the following. We have some reference frame as before, and we have a vector R, and we have some, we make here some small box. And inside this box, in reality, maybe we have many electrons or maybe protons or some charges. And we simply count the charges inside this small box. And then this box has a size. And this, in this course for Ryan-Griffiths, we will denote by delta tau. So delta tau is an element volume in 3 dimensions. Maybe you can write it, for example, in Cartesian coordinates, dx, dy, dz. But we prefer to write it as delta tau, as some notation that is contracted. And rho of R times delta tau, this is simply the total charge inside the volume of size delta tau. Now, you can ask yourself a kind of physical question. What is the correct description? So maybe you think this is the correct description. And what are we doing here? So in a real system, more or less real, we have some body, can be extremely complicated. And microscopically, we might have charges in here which are discrete. Now, if you think about this for 1 second, what you will say, let us look at some point close to a charge here. What will be the electric field? It will diverge because of Coulomb's law. We don't care about these divergences. So we have these divergences on this microscopical scale, and we kind of smooth them out. What does it mean, smooth them out? If I have a continuum description, the same body is a continuum. At this point, close to some microscopical charge, we'll have no divergence because we are smoothing out the field. So when we talk about a smooth distribution of charges in this continuum description, and we are calculating some electric field, what are we actually calculating? We're not calculating a microscopical field that might diverge in some points is on the charges, the microscopical charges. We are actually calculating an average field on a small volume. And then you can ask, why? I have an infinity at some point and I throw it away. What type of thing is it? Imagine that in this classroom there will be one infinity of your height, and I average over all of you. Can I throw away an infinity? And what does it tell me? So this is something you need to think about. I mean, what is the meaning of this thing? So then you can ask yourself also, let's say I want to measure this field. Can I come with a small stick inside and measure this electric field close to this specific charge? So the measurement of the electric field of such a body is actually itself an average. It's not, you're not measuring usually the microscopic field at a given point, but you are smoothing the average. So when I have this formula, when you think about it in a microscopical term, this rho of R is a smoothing, it's a coarse graining of the microscopical description. it is same, I would say, for the electric field. And actually, we are looking here at something which is an average quantity, coarse-grained quantity, which is still a fantastic approximation in most devices because also the measurements cannot go into the microscopical thing. So the microscopical real world, the complicated real world is really hidden from our eyes in macroscopic measurements. So we're taking this in mind, we are going to consider these two approaches, discrete and continuum, and this will depend on what is the physical model. Okay, so let us now, so here I describe briefly the main equations according to Maxwell, but there is a famous, well-known description of the electrostatic problem, and that is due to a French guy called Coulomb. So Coulomb's law is morally equivalent to this. It's not anything different. And Coulomb can complain, why does Maxwell steal his fame? Well, it's not because of that. Maxwell became famous. He became famous by the whole set of equations. But essentially, Gauss and Maxwell here in this case are the same thing as Coulomb. There's no difference whatsoever. I think you know this, but let us stress this. So what is Coulomb's law? This is the most basic law that you learn in high school. So let us write it down in a slightly more advanced way. In university, you make simple things complicated. So you have here some position R, and I want to know what is the field at this point. This is the observation point that I want to find the field. And then I have some source. So this will be denoted by R prime. This source is what is a charge that is creating the field. And there is a distance here. This vector is going to be important, the distance between R and R prime. I denote this one with R prime because I'm thinking already about many sources here. And eventually this R prime will be, what will it be? Integration over all space, over all the charges, and this is similar to the sum that we have here. Instead of summation, we'll do integration. So what is the electric field? This is given by, okay, I wanted to do it all in red, but this is given by this 1 over R 4 pi epsilon 0, an integral over the volume. And when I say integral here over the volume, it will be confusing sometimes. What is this volume? The volume here is all space. Sometimes we'll integrate over part of space, but this is integration over space, and I write it as one integral because I'm very lazy. I don't like to write dx, dy, dz. I am using this d tau trick to shorten the notation. I'm now helping you get used to this notation used by this clever teacher, Mr. Griffiths. So we have here the density at point R prime. These are the sources. And then we're going to write here the Coulomb's law, and we're going to write it like this: R minus R prime. This is this distance here. And I'm going to write it in the following way. I'm going to write it as D minus 1. And here I need to have the vector, of course. So here I have R, look, never mind, I like colors. R minus R prime d tau. And this is the well-known Coulomb law that you all learned in high school. And what is D? D, as someone mentioned here, it is the dimension. So what is D? Usually D is 3. We are working in a 3-dimensional world. So we have a 3 minus 1, and even I know what's 3 minus 1, that's 2. And that's the famous 2 from Coulomb's law. But the fact that Coulomb's law has this d minus 1, the d minus 1 here comes in, it actually builds all the theory. It's all based on the fact that you have here 3. All this comes from there. All the laws you know comes from there. I'll demonstrate it soon. But where do you have d minus 1 in another thing that more mathematical that you always use? This is, by the way, d tau. Where do you know d minus 1? R d minus 1? I mean, it's in d tau. When I do integration in 3 dimensions in polar coordinates, I have rd to the minus 1. Usually it's r to the power 2, dr. And this many times will cancel and create all kinds of things. So we are extremely lucky to have R3. And this, as I mentioned already, we will emphasize this. So, yeah, so this is the vector. This is already becoming a bit indigestive. And then we have this integral. Now, I think you understand why this holds. Why this holds. It holds in a microscopical world. If I take this density, it's a sum of delta functions. So if I put this density here inside here, I'll have a sum of delta functions with all kinds of charges all over the world. And then each delta function, what will it give you? The usual Coulomb law coming from the specific charge Qi. So this equation and this equation, they have to come together. And then you just see the Coulomb's law. So what is this Coulomb law? Actually, it's not only Coulomb's law. It's Coulomb's law and another law. This is a combination of two laws. So, exactly. So this actually we put under the rug, so to say, two laws. One of them is the Coulomb law that is actually dealing with two charges only. That's the simplest case where you have one delta function here. Sorry, you have, when I said two charges, I meant you have a source, one source, and then maybe a tracer that is feeling that source. That's what I meant by two. So there's one charge creating the field. That's the usual Coulomb's law, which is, of course, well known. Here I'm using a sum because of this delta function. And then I'll have contributions in principle for many charges if I can do this integral. Now, this integral is not a trivial integral in general. It's a formal expression because I have to do this integral over d tau. And you see I have these positions of these sources, r prime and r. And you need to calculate all the vectors. Oh, this is horrible. This integral is, I can write it as in the universities. To calculate things with this directly is very complicated usually, and we do not do that. What we usually do is we go to a potential field through Poisson, and then we will calculate the electric field. Oh, by the way, this is a vector, of course. So what is r minus r prime? This object is a unit vector in this direction of these new vector, which is the difference between the position I'm looking at and the source. So this hat means unit vector in this direction. And of course, this unit vector is changing when I'm integration over r prime. Okay, so this was a formalism of Coulomb plus superposition law. So what is superposition? It means that I have one charge here, I have another charge here, both of them are creating a field there. I take one of the charge, create the electric field, take another charge, create electric field, and the two charges, you simply sum them up vectorially and get to the field. It's not totally trivial, because it could be that if you have one charge here and another charge here, this charge is influencing that charge and then changing the field over there. But superposition, and this is why I say superposition is in addition to Coulomb, which is just the force between the two particles. It's not obvious that it is, but okay, you got used to it, so it's obvious for everyone. But when you think about it a bit, it's not totally obvious.
And
yes.
When you say the density is like you say like a superposition of infinite number of charges?
Not necessarily. No, there's not infinite amount of charges in the world because our world is finite.
Like
so I'm jumping. I don't know exactly what is the question because it's a statement, but let me try to answer anyway. I have in my mind at least two formalisms, continuum and discrete, and I jump between them depending on my problem that I solve. in a discrete problem, I have a finite amount of charges, and then you sum up vectorially. This integral will turn into a sum of terms, and these will be vectors, and then you'll add them up, and in principle you'll get. But usually you'll use the continuum where you have here a smooth function. A smooth function entering, you do this integration, and then you get. So what is the question exactly?
No, the question is like how you go from the discrete to the continuum. Like you imagine as an infinite sum of particles like next to each other, or
imagination. Okay, so it depends on the physical problem that you have in mind. If some guy tells you, I have a fixed charge here and a fixed charge there and another fixed charge there, then you use the discrete description. And if some guy says, I give you the density, which is a smooth object, or if you want to think about it, then you use the smooth object. But you need to know that if you go inside the object, then you'll see the discreteness eventually. That's all.
And another question that comes from this is, if I see like I have this classroom and I have a small density here, can I approximate it as a discrete? Like if I consider the volume as much bigger than
okay, so in some cases the answer is yes. And you know this, I think, for example, a well-known example is, let's say you take a sphere and it's a continuum charge on it. But now you want to look at there is some total charge due to some density. It doesn't even matter how you distribute the density in the small ball. You go far away, what will be the field is very simple. It will be simply Coulomb's law with the total charge in here. And this is exactly what actually I was telling you why there's an issue of coarse graining. When you go far away, if I go far away from this world, what do I see? A ball. I see it's like a point. The further I go, the better I see. If I'm close by on this planet Earth, I see hills, valleys, rivers, etc. So these details obviously locally are important, but when you are far away, they're not important. And this is how you can go and smooth things out. It's something I think very intuitive and very interesting, because I'll come back to this later. When we will calculate energy of discrete and continuum, there will be some subtleties. So that will be the interesting part of the discussion, but that will come much later if you don't ask too many questions. So epsilon 0 is given, as you know, by this number, 10 to the minus 12 Coulomb squared Newton meter squared. So these are, now I define the units that we are using. We are using Newton meters Coulomb. And this is the permittivity of the vacuum of free space. So this is called permittivity. In Hebrew, it has a different name. קבוע דיאלקטי של הvacuum. So I don't know why this is here permittivity in English. So in general, this is a remark. We don't need only rho. That rho will be denoted in 3 dimensions, but we can have sigma and we can have lambda. And these are all charge densities. So sigma will be, you have a surface. So this is a surface. So sigma has units. This is 1D, 1 dimension. Sigma has units of 1 over meter squared. Lambda has units of charge over a meter. So this is this will be denoted by lambda. They will have some charge on some object, but all of them are of course embedded in 3 dimensions. It's not that we are changing the dimension, we are changing the charge density. And then instead of integrating, if all the charges are on a surface, we need to replace this rho by a sigma. And if it's a surface in 1 dimension, we need to replace this rho with some density, which can depend on where along. So let's say this is a DNA, and here you have a lot of charge, and here's not so many charges. So this density can change. So this rho can be many different things, actually. And in Griffith's book, you will see all kinds of examples. I'm not going to discuss them right now. but you should have this in mind that we can have different types of problems where we replace rho. Okay, so now let us briefly discuss some consequences of this. So one consequence is that the simplest consequence, which is very useful. So as I mentioned, this equation is ugly, and actually electric fields are in some sense ugly, because what do we have here? We have here in Cartesian coordinates, we have E, which is in x direction, E in y direction, and E in z direction. So E is E of x, EY, and EZ. So I need to calculate three functions. And these three functions depend on three coordinates. So wouldn't it be nice to replace it by one function? And this function is called the potential. The potential field is a scalar. So we have this potential field. In general, this is the potential field, which is useful because a potential is simply a scalar, and it's in that sense it's much easier. It also gives you information on work and energy, etc. So the idea is very simple, because the mathematical idea, curl of E is equal to 0. So once we will go back to dynamics, where the magnetic fields are time dependent, then we have to think about this. Then we'll have also all kinds of magnetic potentials, things like that. So because of this, immediately it follows, and I'll show it to you even, that you can write E as the gradient of V. There exists some function V where it gives you the E. Now you can claim, it's not so difficult. It's not that V is easier than E. The assumption here is that taking this gradient is easy. So differentiating a function is easy. So if I can calculate V, I can immediately get E. This is not a problem, the last step here. So I should calculate V instead of E in some cases. And this rotor of E equals 0. We can prove it in two lines. This is just x, y, z, ddx, ddy, ddz. And this with the minus sign, and here I'll write it like this: Vx, Vy, Vz, where Vx is dx, V. So I just wrote the definition here of the E. Here I have Ex, Ey, Ez together with this minus sign. And then, for example, this rotor is giving you a V. In the x direction, it's giving you Vyz minus Vzy. And then there are other terms which I'm not going to bother, but this guy is obviously equal 0. And this is exactly what we require, so this is equal 0. And what is Vyz? This is the derivative of V, the potential with respect first to y and then to z. And what is Vzy? It's the derivative of the z first and then the y. And you can change the order of the potentials, and mathematicians will prove that you can do that, but we know that we can do that because we assume that the function V of r is smooth and nice. So it's very easy, and you all know this, that we can use this potential in order to satisfy only this law over here, that the curl of E is equal 0. Why did I show you this thing that you know? Is just to mention that all these curls, all these divergence theorems, all these things, this is in chapter 1 in Griffiths. And you should read chapter 1 in Griffiths if you don't remember how to do a line integral, if you don't remember how to do a surface integral of a dA or dL. All this thing is chapter 1, and I'm not going to teach you chapter 1. It will be a little bit in your homework, but it's something that you are meant to read, and you also must know what is a curl, you must know what is a divergence, and you must know all different coordinates units. I'm not teaching this, but I'm assuming that you know this, so I'm going to just write it down because I think you saw it in maybe a million courses in the past. Okay, so now you can do this. Of course, this is correct, but you can also build some intuition, or I would like to build some intuition. And it's very simple intuition, and that is based on field lines. So you can see this. And what we are going to do is we are going to use one charge, and I'm going to put the charge in the origin. The reason why I'm using one charge, because if I prove it for one charge, show you that this curly is 0, then by a geometrical argument, of course, you know it's 0, then I can prove it for any set of charge because of this magic word superposition. Oh, that is very weak now. Okay, so we just put here a charge, and what do? We put here the field lines. I'm going to explain or remind you what are these field lines soon. And I'm doing this in a plot which is in 2 dimensions, but actually you need to think about the sphere that is coming out of this wall, and the field lines are also turning into your direction. So if this is the source, then all these lines are going out of the source. Now you think, okay, this is the field lines, it's trivial, but actually it's not trivial at all. Okay, maybe you think it's trivial, I don't know. But it is both trivial, and there is something very nice here, because what are we doing? We are showing the directions of the lines, which are obvious because Coulomb's law for one particle go outside. So this is obvious, these arrows. But how do we see in this picture, how do we see the strength of the field? Because if I wanted to plot the strength of the field, let's say we live in the modern world, maybe I should plot it like this. I mean, this is what I would do. Of course, Maxwell didn't have all these things, but I would say, I want to plot the force. So, okay, here I'll write it as kind of this color, and then I'll do it like that, and then like that. Why? Because at the beginning, the field is strong, and here it's weaker, and here is weaker, and then I'll have this line, and then I'll have this line, and then I'll have this line. This I'll say strong. It's like the story with the 3 bears, you know, strong, intermediate, and weak, and so on. I'll plot it in like this. But you see, okay, we don't do it. We do it like that. So why is this possible? Why is this possible? Why can we plot it like that? Or what is the meaning of this plot? Yeah?
The density of the arrows are the same.
Right. So I'll explain this, or I'll remind you here. The reason is that we are working in d equals 3, which is the same as what you said. So again, we see this. So the idea here is the following. We can see the density in these plots. If I look here at a circle, and I call it the small circle, and then I look at a big circle, this is a theoretical construction, small and big, then the number of lines, and this is a choice. You choose how dense your lines are. You can plot more lines or less lines. This is up to you. The number of lines going through these 2 actually spheres is the same. That's the law of conservation of lines. It's exactly the same amount of lines. But the issue is exactly as was mentioned, that the density here on the outer line, outer ball, and the inner ball will be different, of course, because the outer ball is bigger. But what is the ratio of the densities? The ratio of the densities is exactly the ratio of the electric fields. So, and this is only because the density, how is the density calculated? The number of lines over the surface of these balls. This is, of course, given by, what is the law? What is the surface of a ball? It's r to the power d minus 1, which is r to the power 2. So the surface here is proportional to, let's say, r big power 2. So the density at surface big. Again, density of what? Density of these lines over the density of surface small, whatever they are, is the ratio. So this is a number, the number of lines that you count them, and this number is the same in three cases, divided by, there are factors of pi and all this, but they will cancel out, so it's not important. This is going to be the RB to the power 2. It's a surface, so the density is 1 over meter squared, not meter to the power 3. And then here we have R small, and this 2 is the same as in Coulomb's law. So this is the field, I mean the inverse of this, 1 over RB field at B. This is the field at A. R small. That's why this field, these plots were very useful before we used all these color plots, sophisticated plotting. We don't need the color. We can do it the old-fashioned way, and that was very lucky because in the old days it would be very hard to plot it with colors, so we plot it by hand. So this is the idea behind this. But going back to this law, from these fields of lines, you immediately see that rotor A is equal 0. I mean, if you think about it a little bit, and you should. Why? Because what is non-zero field? It can be a velocity field, for example. For example, you sit in your bath and you look at the water going down the drain. It circulates, right? There is some curl there. So essentially, a non-zero field, V not potential, some velocity field with rotor V not equal 0 will look something like, for example, like that. Or for example, you have a person and he has some hair and it's curly hair. So here, rotor of the hair is not 0 because there are these curls, and that's why the curl is called the curl. Your head has a lot of curl. My head, it's even not a scalar. Okay, and on the other hand, if you have a person which is looking something like that, and its hair diverges, but at least at this point, there is a divergence. You see the hedge is diverging like that. So this is dV is equal 0. It's similar to what is happening here. It doesn't mean that he doesn't have a little bit of curl here. And of course, if you have nothing on your head, then okay, then both divergence and curl are 0. That's obvious. So you see by the force of lines that this field has no curl. This is the meaning of curl, intuitive meaning of curl. Okay, so now you remember what is curl intuitively and non-intuitively, mathematically and more physically or with pictures. So now we can go to the main conclusion of Griffiths on all of electrostatics. So let us summarize. The idea of Griffiths is the following. We have a density, which is a scalar, of course. We have electric field that many times we are interested in. And we have a potential field. And there are relations between these three objects. Some of them we already gave. For example, the relation between rho of R and the electric field is given here. So let us summarize these relations. And the idea is, generally, you have all kinds of problems. You can go from rho to V, or from V to rho, or from V to E, etc. And there are different equations describing this. And let us just mention these equations. And just the general structure of the theory. So we have, if we want to go from V to E and backwards, potential to electric field, this is something that we mentioned already half. So we have already the definition, which is E equal minus gradient of V. So this is differentiation. This is a scalar and this is a vector. This is mentioned already. And then we can go, of course, delta V is equal minus from some point A to B E dl. So we have some electric field along a line, and we integrate in order to get the difference of the potential between point A and point B. So this is the opposite of this. So I think this one is trivial, or it's known. This is integration. And of course, integration or differentiations, of course, they are related to one to another, but in many cases, the integration is more complicated than the differentiation. Then we have this rho going to E or vice versa. So this is a scalar and this is a vector. And also here we have a differential law, which is given by this. And we have the Coulomb's law, which is integration, which was already given, but let us write it again. D tau of R, R minus R prime, four pi epsilon 0. And here there is another law, which is related to this one, and this is called Gauss differential law, and then there's also Gauss integration law. We will soon give it, but you can use also Coulomb in principle. And the new thing now, or semi-reminder, is to go from potential to density. That's what is left. And this is easy now. This is the reason why I wrote all this thing that you know, because you see what is going on here. I can take use this operation, this del operation on E, that will give me this divergence, and then I'll use it also here. What will I get here? Laplacian. And Laplacian is related to a famous equation, which is Poisson. So the Poisson equation is also differentiation. So it comes in this line, minus rho over E0. So you immediately see from these two laws, you get this one. And as I mentioned already, the advantage is now you're going from a scalar to a scalar, which some people like. That's the advantage. But is it really an advantage? Well, it's second order. Because it's second order, it's a bit harder than a first order that you have here. So we will discuss later how to solve this equation. This will not be in this class. And what is V of R? Well, you can write it in Coulomb's law, like you did here. And this is simply 4 pi epsilon 0, integral d tau, as before, rho of R prime. It's a vector. And now I have R minus R prime. And that's it. So instead of the 2 here, I have 1 over the distance, this one. And this is also something that you know, at least for a point charge, that if the electric field decays like 1 over R to the power 2, the potential decays like 1 over R. And the only semi-new thing that I think you also saw this before is that now I do this with an integration over all the sources that are here. And I denote it here with this d tau. Now, what will be easier or difficult to solve in different problems, it depends on the problem. Many problems, usually if you can solve problem with one method, you can solve it with all method. And if you cannot solve it, you cannot solve it with all method. But there are some maybe special cases where you can solve it with one method quite easily and with others not. So you need to know what is your poison, which tool to use to solve different problems. And you need to understand, for example, especially here, what are the boundary conditions? The difficult part in usually solving these equations, especially when you do integrations, So very generally, you know that when I have a function and I differentiate it, let's intuitively say it's an easy operation. When I integrate it, I always add one integration as a constant. If you have two integrations, two constants, etc., etc. And then these constants are usually not given in problems. And you need to think, where do these constants come from? So usually they come from boundary conditions. And that is the difficult part usually of this integration part. How to determine these constants based on boundary conditions. Beyond the difficulty of, solving things, of course. It's not generally easy. So let us continue with some geometry. I like simple geometry. Let us now go back to this integration of the EDL. It comes from a well-known law that if you have an electric field and I integrate EDL over a closed path. So here I'm now going, this I think symbol sometimes is an integration over a surface and sometimes over a closed path. But this guy is equal 0. This is related to the fact that the rotary is 0, and this is the fact related to the fact that the forces are conservative, which means if I go over a loop, if I think about E with some charge, I put some charge along this loop or along this trajectory, then the total energy is going to be 0 when I come back, because there is no input of energy and there is no dissipation in this problem. So there are many ways to see this, but let us just think how we can prove it easily by looking, not by proving. So again, we are going to use one single charge. So I have the force fields, the electric fields, and they look something like that. And then what is the simplest path, which is an example, to show that this is 0? It's trivial. You're going to take a circle, because this is my path of integration, the closed path that I had here. If I do EDL here, the answer is 0, and this is trivial. Why? Because the angle between E and DL, what is it? This is DL here, this is DL here, this is pi over 2. It's always, and then when you do the integration, you get 0. Okay, so this law in this path is trivial. Now let us consider a more general path, and then we'll have some intuition why this is correct. Let's distort this path. So I want to think of a different path. A mathematician might say not the most general path, but still. It's not general because I'm going to limit the path in 2 dimensions in a 3-dimensional space. So I'm going to use, again, I have only one charge. So this is, the charge is here. So this is all for one Coulomb's law. And then what I always do, superposition, I can do it for many charges. It will be the same because each path of each one of them will give me the same 0. There is an issue is if it's moved, but okay, I'm not really proving here. But let us define a new path. So we have this charge here. And now I'm defining this path of integration, and I want to do it something a little bit crazy, maybe something like this. And then I want to go, these are all, these are very bad drawings. Something like this. The idea here, I'm using not the most general path, but this is the center here. This is the center here. This one is in the center here, etc. This one is a small arch. I hope you understand. Now let us ask what is EDL along this crazy path. And I claim it's easy to see that is 0. But how do you see that?
Separate the part.
Right, so we start, I think that's what you want to say. Let us start with these lines. these are arcs, and of course this one. All these ones are trivially 0, exactly like before in this simple example, because along this case, EDL, the angle is like before, pi over 2. But what is happening along these lines? So, okay, these lines are very bad. I meant to write them like continuation of the radius. I'm a very bad painter. Yeah, maybe I should use some new techniques like ChatGPT. So anyway, okay, and this is also wrong. This is actually wrong. This I don't want to write it on this line. So let us also denote the integration path. So we're going in this direction. And then we have here 1, and here we have 2. I already took care of these arcs. Here I have 3, and here I have 4, and here I have 5, and here I have 6. And the idea, which I hope you all see now, maybe you don't see, what do you see? That all these integrations, now the angles, what are the angles? The angles are now 0, so they're in the same direction here. In my very bad drawing. So along this line, E is parallel to dl. But the idea is if I integrate over here, I get an integral I1. And if I integrate here, I get I2, and then I3, and then I4, and I5, and I6. And I also assume that this radius and this radius are the same. So I1 plus I2 plus I3 plus I4 plus I5 plus I6 is 0. The reason is I'm going along a length, some length. Here I'm going another length. Here I'm going another length. Here I'm going another length, etc. But the point is, because of the charge here, at a given radius, the electric field is exactly the same along these rays. And then when I integrate, I'll sum over all these integrations. And if you don't understand immediately, you should think about it a bit more. And the sum over these integrations will give you 0, and then you are done. Why this is not a mathematical proof. We have a mathematical proof from this. Why am I done? Because this is, okay, this is a particular surface that I draw here, but I can essentially, any line that I want, I can combine with small arcs and small ups and downs to a good approximation. And then it's trivial that you see this. So immediately you see that this rule is applicable. And you also see maybe something else, that this is not specific actually, as far as I think, it's not specifically to the 1 over r to the power 2. It could be for some central field, because as long as the field here and let's say this point on the same radius are the same, the integrations will cancel out along these lines. Okay, so this was a little bit on this. So then we can go on and remind you how, before I had these connections between different presentations. So let us see how you, or remind you how you prove it based on a useful identity. And that is, how do you show that these simple Maxwell equations for electrostatics are equivalent to Coulomb's law? And this is based on one identity, essentially, which is relating the Coulomb potential to a delta function. So let us do this. We have dr E. So this is the Gauss law, if you want. But what I'm going to do, I'm just going to plug in here Mr. Coulomb's law. And I'm doing it only for a single charge. And then I argue, okay, if it's for a single charge with superposition, it will hold in general. I'm doing it in the simplest case. And then you have here an you have here, okay, no, I'm doing it in general. Sorry, I made a mistake. I have here r minus r prime. And now you know already what is the meaning of r prime. This r is the position where the field is. R prime is the position where the source is. Here I have r minus r prime, and here I have rho of r as before of d tau. And the integration is over all space, wherever you have charges. Of course, if there are spaces in, there are locations in space where the rho is 0, then you don't need to integrate over them, but in principle, over all space. So the whole idea is that this object here, so believe me for a second, is 4 pi delta r minus r prime. And this is a mathematical identity, if you wish, related to the fact that we have here a 2, which is b minus 1. And then if I integrate over a delta function, this is a delta function in 3 dimensions. Even I can integrate something over a delta function. The 4 pi here will cancel this 4 pi, and then we get the Gauss law. So what you need to do is to say, if you want to start with Coulomb, this is Coulomb, you take this, you take this divergence, and then you get the divergence of E, which gives you, this rho of R. That's all. And this is what I said before, that the two laws are the same. The only issue that I want to remind you is why this is happening. And this is an identity that I'll now show you quite not so rigorously, but good enough.
This is a nebula, right?
This is what?
DR.
So what oh yes, thank you. I wrote the R because we are going to use soon spherical polar coordinates. It's you don't need this, but I prepared you, so
thank you.
I will sometimes add these notations just so. The proof, we are not going to prove it with the r prime. We are going to use r prime equals 0, but it's the same when you have this r prime. I'm going to leave it to you. So the claim is, the mathematical claim is the following. Okay, without an r now. R hat r squared. This is a delta function of r multiplied by 4 pi. So what I did here, I took the r prime to be 0, but then if it's not 0, you just shift it here. It's the same thing. And this is the following. Now enters the fact that the most, so now this delta function, of course, is on the origin. So if you want to think about it physically, this is the Coulomb's law on the origin. You have a charge. Now, to prove this is rather easy because of the direction of this field. It's in this r prime hat direction, because then I don't need the full expression for this divergence. I need only the part of it that is related to the r direction and not the theta and the phi direction. So that's, of course, very useful. So this is simply r squared. This is simply 1 over r squared. Here I'm using a well-known formula, r squared, 1 over r squared. So the idea here, this comes from the divergence. This is part of the divergence. This comes from Coulomb's law. And you see r squared over r squared, and this is what I said before, that the dimensions are the same. This is all related to the dimension. This gives you 1, and then you have here d over dr of 1, and that is 0. But this is not a delta function. So this is valid, however, only if r is not equal 0. When r is 0, we need to be a bit more careful, and we will show that it is a delta function, because if r is going to 0, 0, you are dividing here two objects, which is not well defined. So this is not a trivial thing, but this function, you see this result. This is the claim already. This function, delta function, is 0 everywhere except for r equals 0. But now we want to show that it is actually a delta function. How do we, as physicists at least, show that it is a delta function? We are going to say, what is a delta function? In principle, an integration over a delta function, which is a function which is 0 in most space, over whole space, d tau, that is equal 1. In principle, mathematicians will also put here a function and show that this is the function at 0, depending or not whether some nice properties of the function, but we will not care about this. So our definition of a delta function here, at least, is a function that is everywhere 0. On the point, it should diverge because the integral gives you 1, and the area underneath this function is 1. That is a delta function for most physicists. And this is easy to prove, because all I need to do is I need to integrate this. So we do that by integration. I need to show this, so I need to integrate over a space hat squared d tau. And how do I do this? Now this looks like a strange integral, right? Because I have a divergence, and then I need to integrate. If I have a derivative of a function, and then I integrate it, it should be easy. And also this one should be easy. And what is the name of the theorem that gives you this integration? Yeah, so this is the divergence theorem. Again, this is chapter 1 in Griffiths. And the divergence theorem allows you, when you are doing this integration in 3 dimensions, to go from an integral of a divergence to an integral over the surface. Over a surface. I need to define what I mean by integration over space a bit better. So, but first let me write this. This is r squared dot dA. So before I said all space, if I said that, delete it from the video, I meant we choose an integration. So let's write it, integration, let's say, over a sphere of size of radius r. So I choose to integrate this function with some sphere of radius r. So this is the point, and here I have a sphere, and I integrate over this. And this sphere, which is it's a theoretical construction, has some radius r. Okay, so if I integrate this, then I need to remember what is dA. This is the divergence theorem, which goes from an integration over a volume, which means all integration here inside. And what do I do here? This is a surface integral, not a closed line integral that we had before. And this is an integral over the surface. So this is inside the sphere, this is on the surface of the sphere. And this is why we have dA, and dA, as usual, if I have a surface here, dA, this is dA, and dA has a direction. This direction is orthogonal, is normal to the surface of the sphere. It's just a point, dA. And this again, this is chapter 1 from Griffiths. And again, if you don't remember, then please go over this, because I assume you know these things. And then here the idea is that the surface is fixed. So this R, capital R, is fixed. And then this integral is going to be simply, the point is that dA and R hat are parallel one to another, because this is R hat is going from the middle R hat. So R hat is parallel to dA, because dA is the normal, and we are using a sphere. We choose a convenient construction. And then this integral, let's call it I, is equal to the following. It's equal to integral from -1 to 1 of d cosine theta, integral from 0 to 2 pi d phi. Here I have r squared, which is this r squared. And then I have another r squared, and this is equal 4 pi. And this is exactly what I used before. So we finished QED. We did this simple proof that the integral gives you this 4 pi. This 4 pi enters, this was this 4 pi here at the beginning. Okay, so we have this description, and then just to close the theory, there is one more basic law that you all know in some form. I just formulate it here in integral form, and that is the Gauss law in its integration formulation. So this is an extremely useful law when you have some symmetry in the system, and it's used to solve all kinds of simple problems in high schools. And we will just formulate it briefly. And the idea is, again, use the divergence theorem as we just did now. And the idea is like this. We have the divergence of E is equal rho of E0. Now, if I integrate this, then I'm integrating a divergence of an E. If I'm integrating a divergence of some field, I can turn it from a volume integral to a surface integral. And that's the whole idea. And we can do that easily by writing that. So using the divergence integral, so some surface, so we have EdA, is from this law is the integral rho of r over epsilon 0 over the volume of what? Here, this is the surface, some surface, whatever surface you want. This is a theoretical surface, and this is the volume of the surface, and this is the surface. So the surface can be anything, some surface, and inside the surface, you have a volume. So here I integrate over the volume of the surface. So here it's only outside, and here is also inside. You have to think about it as a three-dimensional object.
You say surface is like the surface of a 3D object.
Any 3D object, any 3D
okay,
object.
not like a 2D surface.
You have a 3D object which is closed, like I'm closed.
Yes.
And then this is my surface. I don't like to integrate inside me. I integrate on the body. Okay, so this is what the divergence theorem says, but what is this object? This object is the Q, the total charge enclosed in the object, divided by epsilon 0. And this is the Gauss law in integration form. It's useful, we'll have a break. For example, let's say you calculate some problem, you calculate the E from some rho by a different way, and then you can check this by integration over the surface, whether or not you made a mistake. So this, if you have some symmetry, is very useful. If you know, for example, that E is pointing in the R direction, some simple considerations of rho, this is very useful, and you can use it in maybe in many useful applications. So this is Gauss integration law, but it's the same as the differential law. It's again in integration. Sometimes it's more complicated, but sometimes it's very easy to do this. Okay, so now we will have a break for 10 minutes, and then we will continue. Let us try and move a bit forward. So let us do a simple exercise. Can we find rho of R such that E is equal So the question is, can we find some density, and I write it as a continuum, such that the electric field is some constant. I don't care about this constant, r to the power b. What do you think is the answer? So the question here is like this: can I modify Coulomb's law by designing some density in 3 dimensions in order to create this field? So what do we know? We know that beta equal 2. What is the charge that gives you this thing? A delta function on the origin, a single charge on the origin. Fine. So a single charge on the origin gives you the Coulomb's law, beta equal 2, the famous beta equal 2. And now I want to have some rho of r, maybe going like that. This is a function of r, maybe going like that. And with that, create a new force field, which is not the beta equal 2. Is this possible or not? What do you think? Is it possible?
No.
Yes, no, maybe.
Maybe
it's not so trivial.
Or the...
No, this is my goal. Yes. And I am asking, can I use some density that we'll soon calculate and find this law valid in all space? Just can we change the Coulomb's law by choosing a very specific charge density? What does it mean? It means there are laboratories in this world apparently, and we will tell the experimentalists, you build a charge density which looks something like that or something like that, and this will give you this field with some b. Is this possible or not? That's the question. Yes?
In my opinion, depends on if it's, כאילו אם זה הגיוני, כי נגיד כאן הגרף שציירת בקוף קו הוא בסופו של דבר מתבדר, וזה לא הגיוני.
Okay, that's a part of the answer, but it's not the full answer. So what he says, if I continue this line, what will be the total charge in the system? It will be infinite.
Yes.
And if I have, so maybe he says you can do it like this. Okay, the answer is a bit more subtle, and let us show why. So the idea here is the following. I'm not going to do the whole math, but let us first look at Coulomb's law. Yeah, it's Coulomb's law. I just write here epsilon 0. Now I have the field. So I can write it as, I'm using here the divergence, and I'm using the fact that this is in the r direction, starting in the origin. So I can write this simply as d over r squared er. What is er? Er here is c over rb. It's er is a scalar. The direction is obvious, it's r hat. And here I just wrote this law like this, and then I have rho divided by epsilon 0. So I'm an engineer now, and I'm asking myself, what is the rho that will give you this E that will give me this answer? And there is a solution to this equation. It's very simple, because we have r to the power 2. I plug in this force, r, this will be 2 minus b. There is a constant c that I don't care about. And this is equal rho of r over epsilon 0. Right, and then I take the derivative. Even I can do this derivative, 2 minus b. And then I take the derivative. This would be 1 minus b. I need to divide by this r squared. And then I get r minus 1 minus b. If I multiply by E0, this is my rho of r. Especially you see here that 2 is special, right? Because here I have 2 minus beta. If I choose beta equal 2, this is a special case. But it's not exactly the Coulomb case because I'm considering a continuous charge. I'm not saying that there is a source. Okay, now I didn't say if beta is bigger or smaller than 0. It can be either bigger than 0 or smaller than 0. If beta is smaller than 0, then we have here an electric field that is increasing as the distance decreases. If beta is bigger than 0, it's decreasing. And then we have this charge. So what is the conclusion here? Based on, first of all, what about rotor E? Is it equal to 0? The answer is yes, because you are in the R direction. So the field looks like something that is going out. So the rotor E is 0. So this density satisfies the basic rules of Maxwell. So if you believe only in Maxwell and you stop there, it can be in principle. But exactly as was pointed out, there is a problem here. And this gentleman pointed out half of the problem. So now let us look. So the conclusion is, according to Maxwell or in general electrostatics, this is possible. But I want to claim this is wrong. That is, you can never find it, and not only for small b and bigger b. Why? Let us look at this a bit more carefully. What is the charge, as was pointed? So the total charge is the integral of a rho of r d tau. The integral over all space. And of course, if this guy, if beta is negative, this is increasing, which is like that, then this will diverge. But what will happen? Let's look at it a bit more carefully. Only b equal 1. You are reducing, but you are wrong. So you're wrong, but you're in the right direction. No. I want to integrate it over all space. So what I'm doing here, I'm assuming that this is valid for all space, from 0 to infinity. This is obviously some idealization. And then I want to integrate over r to the -1 minus b, r squared dr. And I need to multiply by 4 pi over the angles. This is the total charge. So what is the meaning of this total charge? I have some laboratory, let's say in China, they have a lot of money. I tell them, you build this density, and then we'll have this 1 over r to the power b potential. Then you have a pile of charges, and you put it in your system in such a way to create this field, right? This is what we are doing here, but then we are asking how much charge. How much charge? Okay, how much charge? We can do this integral. What is this integral? This integral here is from 0 to infinity, r to the -1 minus beta dr. What is this? It's always infinity. Whatever beta you choose, it's infinity. But there is a difference between different betas. I hope everyone sees that it is infinity. What is your poison? The poison can be either the lower bound or the upper bound. So if, let's say if beta b is less than 2, 2 is again special. If b is less than 2, say b is equal to 1 for simplicity, the lower bound is not a problem, but the upper bound is, because here I have a constant, and then the integration till infinity gives you infinity. Say, so the upper bound is problematic. If beta greater than 0, for example, b equal 3, then I have here r to the power -2. Integral over r at lower limit is diverging. The lower limit, bound, I call it bound, but it's problematic. So no matter what happens when beta is equal to? It's lambda. And ln of 0 is?
minus infinity.
And ln of plus infinity?
Infinity.
So what happens with beta equal 2? The problem is in both sides. So it's always a problem. Of course, okay, beta is special because you have 2 minus b. What I mean by that, if you are a mathematician, let's say the c is 1 over 2 minus beta in this limit or something like that. Okay, so we see that we cannot create this system. So sometimes the Maxwell equations are not enough to make common sense. You need to add more constraints. There is another constraint. Let us assume you have infinite amount of charge. What is another constraint in this type of buildings of idealized fields? You are a practical guy. You want to, let's say you can move charge all over space by input of something. What do you do? How do you do that moving charge? You need to put in some input. What is the input? As usual, it's energy. You move charges, you need to put the energy. So the claim is that also, let's say you add an infinite amount of charge. The amount of energy to build the system is also diverging. But to understand that, we need to understand what is the energy to create a system of charges. And what do I mean by that? You have to imagine the following. I have free space, there's nothing inside. And far away at infinity, I put some amount of charge, a lot or not so much, and then I bring it to some place in space. This process will take you energy. And then we want to know how much energy. You need to invest this energy. And this is what I'm going to discuss now. And I'm going to show you a beautiful theorem that is actually related to the electric field. But there are some subtleties related to these divergences, in some cases, even the simplest case. Yeah.
Because we already learned electrostatic and we know that energy is like potential, but potential goes like 1 over r, and the field goes like 1 over r squared. So they are both infinite, but one is more, כאילו הכוונה שלי שהאנרגיה תהיה גם אינסופית, אבל יותר קטנה.
So no, first of all, energy, you think you understand it, it's more complex. So I'm talking about the specific energy of creating the system. There are different types of energies. So you can have, for example, a set of charges. So, but I'll answer your question soon. So, but my point in all this discussion is that energy is not trivial, and there are different types of energies. So let us start, and I'll answer you, and if not, you can ask me again this type of question. But again, I'm trying eventually to reach the question of how do you build a system, not the energy of one particle in an electric field. That's what you were talking about. It's different. And that makes a confusion because you have some notions, but there are several notions. And this is what I'm trying to clarify here. It's not maybe totally new. So the thing that you all know, this is a reminder, let's say discrete system. So I'm also going to show that this energy concept are actually different for discrete and continuum systems. When you go to discrete systems, you have something very special or interesting or maybe boring for you, I don't know. So let us say the following. Let us say I have here Q1, for example, Q2, Q3, and this is something I think you all know. You have some set of charges and they are discrete. And then you want to go from point B along some path to A with a charge which I'm going to call Q. The capital Q is a tracer Q that is coming in addition to these charges, and I put here some nails so these charges are fixed. And then I go from A to B. Usually A comes before B. And this is well known, and I think you know this, is you go from A to B. W is for work, and this energy, and this is simply given by FDL. And I'm going to write it as QVB minus VA, and there is a sign problem here that you need to think about it, because is it the energy you invest or the energy you get? But I'm going to write this at this stage as absolute value. Just to forget about there are different notations of if you put it in or you don't. And I think you all saw this issue, and it's where does it come from? It comes from the fact that this F is proportional to E and to the electric field. What is the proportionality? It's this Q, capital Q. And then when I go along this path, I'm actually integrating over E, and then I get this potential difference. This is what you know. This is given a set of charges, but I'm asking a different question: how you build this system and how much energy is inside, how much energy is stored in this in the process of building it. So the claim is, but here simply the general formula is that this is, okay, so first of all, let us take, we want to start at infinity. If we start at infinity, this is R equal infinity, then I'm going to use V infinity is going to be equal 0. This is a convention. There is a very far distances, the potential is 0. And if I start there, this one is 0, then you have this famous equation, Q is equal V of R, and then I can, in principle, calculate from all this set of charge the V of R in some place B. Now I come from infinity, and then I'll get this well-known equation. But what I want to discuss now is something a bit different. I'll use the same letter, but this is this. What is this? Discrete. This is the energy of creating the system. It's not the same thing as moving one particle in a system. So this I claim, and I'll soon explain why, this is equal the following. In discrete world, Qi VR sum over I equal 1 to N. There is a little chupchik here, and this is the following thing. This potential, so this is a claim, and soon you'll see why this is useful. I take one charge, let's say Q1, and I calculate VR on the same charge. That sounds stupid. What is this meaning of this V? You have this chupchik. This V is the potential without this guy. The potential that comes from all the other people. What is the logic here? When these are set here, and I'm going to bring, let's say, Q1 from infinity, he cares about the other charges in the creation of the total energy of the system. Then we'll have to show why this is half. I'll show you. So I hope you understand that there is a big difference between this guy and this guy. And this chupchik is very important because you exclude in calculation of VRI, the charge on Ri, obviously, because that will give you infinity. I mean, it's a good thing that we have to include it, remove it. So how does this equation, which I think maybe you also saw it somewhere, how does this equation, how is it constructed? It's easy. Let us do it slowly. So we start with a system which is empty. I'm building the system. And I'm going to use only 2 particles at the beginning, but I think later you can easily extend it. So here I have a vacuum. Where are my 2 particles? One of them is here and one of them here, far away at infinity. They are not interacting there. So the energy here is at the beginning is 0. Now I have one of them and I bring it from infinity. So this guy came and I put it someplace. I bring it from infinity. How much energy did it cost you? Nothing. Because there's no other charge. He's not working against any field. He's just moving in a vacuum. It's very simple. Now, when I bring the second guy, I have one of them which is already here. I nailed it to the wall. It's not moving. And then I bring the other guy. So this is particle 1. So bring second guy. This second guy is feeling the potential created by the first guy. And this is the first equation that we already had. It's exactly the same when we brought in the second one. So now we just want to explain this trick. So obviously, okay, what is the work here? This is obviously Q1. In this problem, it's very simple. Q2, R12, and you have the usual 4 pi epsilon 0. This is exactly what was mentioned before. You think about Q1 as fixed. I bought Q2. So all this object is simply the potential at a point 1, 2. That's the distance between these two particles here. And that's it, right? This is very simple. This is what we told you. But now a small trick. Let us write it as like this. It sounds, at the beginning, it sounds maybe even stupid in this case. But I can write it as Q1 VR1 plus 1 over 2 Q2 VR2. And what are these two potentials? These are the potential created by, it's becoming late, so I don't remember if to write in Hebrew or in English. Potential created by 2, and this is the potential created by 1. And the half here is obvious because I just write it 2 times. So the question is, why do I do that? Of course, with 2 particles, it doesn't make any sense. And now we are going to continue with this, and we will see how we can calculate in general. So in general, the formula is just you need to sum. Yeah, I already wrote it here. This is when you add 1 more particle. If you continue this process, you'll get this general formula. So up to now, I explained to you in principle how you calculate the energy of creating the system. But in our problem before, we had a continuum distribution. It's not the same thing. So how do we solve the problem when we have a continuum? Well, the answer is basically, what do you need to do? Here I have a sum. If I have a continuum, I have to change it to an integral. But there are some subtleties. So let us do that. I will follow Griffiths, who does this. And I want to introduce a new notation. So now I'm working with continuum charges. So we have some rho of R, which is a smooth function. And then I'm going to define W of creating the system as a function of the electric field. This is not going to be clear right now, but soon it will be clear. And the idea is that this is the same half that we had before. And now I need to write this like that. Integration all space. So before we had the sum, I'll replace the sum with the density function that you can think about as a sum of delta function. It will give you this. And there is a very subtle issue here, and I don't call this the same as the discrete energy because of a problem. So I call this the density, the charging for a continuum. So I hope you can see that this is more or less the same. But now comes something beautiful, and that is I can relate the density using Maxwell's equation for electrostatics with the field. So here I write the basic equation. I multiply it by epsilon 0 to the other side. This is the rho that you have here. But what is V? That's the potential. What is V? V is also related to the field. So now I'm going to slowly, we are marching to the fact that the field itself, if you know it, you can have the energy. So the field, which always gives you the force, inside this field, which is a little bit abstract notion, what is the field? If you know it, it contains energy. The energy is in the field, the electric field. So let us see this. It's now simple math. This energy of creating the system is 1/2. Let us do it a bit slowly. So we have here V d tau, all space. So here we really do integration over all space. So let's say rho is bounded in some domain. So the integration is not over all space, but now I'm looking at other places where there is an electric field. For example, imagine you have a system like this. I now have E, and I have rho here. The first integration is inside here. The second integration contains all space, not only inside with the initial density. So here the density is 0. You don't need to integrate here, but now I'm going to integrate also there. And then this guy is equal to, okay, so now what do I need to do now? I want to take this V and create it into an electric field. So how do I do this? This is similar to integration by parts, but in high dimension, because I have here the divergence. I want to put this divergence on this scalar, then I'll get the electric field. So you need to think about when you do integration by part, you have a term that depends on the boundary condition and a term that is moving this thing, and then integration by parts in 3 dimensions is going to give you the following. WE is epsilon 0 over 2 minus minus E. Now I'm moving the divergence onto the V, that is turning the divergence into a gradient. That's the integration by parts here. I'm still integrating over all space because it's not related to divergence theorem, don't be confused. Plus an integration over the surface. Where is the surface? It's at infinity, actually. So this is a surface term, which is VE dA. If you remember integration by parts, this is in 1 dimension. This comes from the lower limit, the limits of the integration. This is the same thing, but it's over the surface. Now, the point is that in general, we're going to assume that it is 0 at far distances. For example, let us assume we have some object which is charged. Now we look at very large distances. This is the boundary term, r going to infinity. Then this V of r, as was mentioned before, this goes like 1 over r. How does E go? Like 1 over r squared. This is E. How does dA go? R squared. And then this boundary term goes to 0 because r is fixed. This is the volume that you take to infinity. What is the divergence of V here? Sorry, the gradient of V. With a minus, that's E. So now we reach finally a very simple and very important equation in physics. Maybe, did you see it already? I don't know. You did see it. Okay, which is E to the power 2 d tau. So this is the final equation, and this integration is over all space. So if I can measure the electric field, then I can calculate this energy. And now you can ask, in the problems I gave you before, what will be the total energy? Because I calculated, I said, you know, this, what was the electric field I assumed at the very beginning? Something that decays like r to the minus beta. What is that squared? That is r to the minus 2 beta multiplied by r squared dr. That will always give you infinity, no matter what. So this was my claim before, that also not only the total charge is, of course, is infinity, which is bad enough, but also the total energy of assembling that system would be infinity. So this is constraint number 2. Let's say in a practical world, you want to say the following: I want to build a field, I have Maxwell's equation, but then I add, these are like the little notes of the lawyers, but with finite amount of charge and finite amount of energy, these two constraints can give you a lot of problems in creating general fields, if you think about it like this. But this is a beautiful formula because it says if I know the electric field, I know the energy of assembling, and many times I can measure the energy. The electric field, usually I have problems to measure it inside the system, which is a problem. But yeah, so this is a kind of exciting formula. But now let us mess up your head a little bit, and then we ask ourselves, what is the energy of a charged single point particle? A Coulomb particle, a simple Coulomb field. What is it? What is this energy?
KQ over.
No, the energy of the integral. The answer is a little bit embarrassing, maybe. Or the man thought that what I did here on the blackboard is not so simple as you might imagine. So assume that you have a field, and we know that such a field, we believe such a field exists. Let's say that E is 1 over r squared, r vector, 4 pi epsilon 0. This is what you learn in high school. This is just the Coulomb field of a point charge, right? So what is the E squared? It goes like r to the power 4. And then WE is going to infinity. So this is the divergence of the energy, and sometimes it's called the self-energy. This is the self-energy of the electron. And in this theory, it's infinity. So what is going on here? First of all, is this physical, or is this a mistake, or what to do with it? These are two different separate things. First of all, is it really infinity? Could it be really infinity? No, maybe. It depends. Maybe God has enough power to build a charge. So the issue is like this. What did we assume here? We assume that you
can go out of the R equals to 0. You assume that you can go into the electron.
Okay, and right. So he has a good point. I'll rephrase it and say if I think I'm saying the same thing. The question boils down to the question: does the electron has a finite radius? Yes or no?
Yes.
This is the same thing, because what did I do here? I integrated. Okay, this is an important point. The blow up of this integral, this infinity, I mentioned before, it could come from small distances and it can come from large distances. If it's 1 over r to the power 4, it's the low limit. This is 0 that I had here in the integration. It's not the far distance limit. So the problem, as he points out, is that at small distances. And then it means, okay, the electron has a finite size, maybe. Does an electron have a finite size? No. We don't know. So the answer is, we can solve this problem. If you want to call it a problem, I'm not sure that it is a problem. It depends on your point of view. Solve this. Assume that electron, I don't say proton because we know the size of the proton, has a finite radius.
Then we just need to make the electron as the lower boundary. Then fix it.
It's a bit more complicated because then we need to say what is the charge density inside the electron, which is a model of that. There's no point in even discussing this for the reason, first of all. So if you ask ChatGPT, what is the radius or what is the radius of an electron? Okay, no one knows, but there is an upper bound. So people know it's smaller than this number. No. This is not theory. This is experiment. Yeah, there might be more advanced theories, but no one can test them, so they are not really theories. I mean, they are propositions. So this is what people know, that it's a smaller than R0. Now, if, for example, we can imagine at least, instead of a point charge, let us look at a charge on a surface. The surface of a small ball whose size is r. Why do I use this model? Because this model is trivial. I'm not saying that you cannot have a charge density inside. I don't know because I never visited inside the electron and no one is even close to this. Because actually, what is the physical reason you cannot explore this is actually because these energies are so high. So to explore it, you need a lot of energy. We don't have this energy, right? I mean, it's beyond our capabilities, even in CERN and places like this. So we can say, let us assume a simplified model where all the charges on the surface. Now, what do we know about, we know this from high school, if the charges are on the surface, they are evenly distributed, the electric field is 0 inside, and it is, what is it outside? It's also well known, it's 4 pi epsilon 0, and here you have Q, the total charge of electron, or whatever that is, r to the power 2, and in direction r. So outside this sphere, it's like a point charge. You don't care about anything else. Now I can do this integration. I'm not going to do it, but it's simple. So now the integration is going to be from r, the size of this small ball, till infinity. You'll have 4 pi. You'll have q to the power 4 pi epsilon 0 to the power 2. And then you'll have 1 over r to the power 4, because this is the electric field to the power 2. And then I have r squared dr. And this is obviously a finite number unless r is infinity. And then this w, the electric field of this simple system, is given by, there's a number 8, which is easy to find, q squared 8 epsilon 0, 1 over r. You can later check what is this number, what is this energy for, let's say, an electron charge in r, 0 of order of this thing, but it will be gigantic no matter what units you use. I mean, so this is the answer. You see that when r goes to 0, this diverges, which is what you expect. Yes.
Is there an intuitive explanation why the energies would be so high?
Yeah, it's very simple. What is the intuition why the energy is so high? Imagine this is the energy of building up this electron. So let's say you have half an electron at some moment in time. Now you need to bring the other half. You bring it together. You put it on a tiny spot. The energy is high because you need to work against the field that's created by the first half.
Because they will repel each other.
Yeah, which is what I was showing you before. If you have these two charges and you put them one on top of the other energy, discrete charges, it will go to infinity. Now the question is, okay, all this infinity, should it really bother us? It depends on your mindset in some sense. Maybe if you are someone from high energy, it should, but in real life, it's not so bad that there is an infinite energy. Why is it not so bad? Because energies are calculated by energy differences. So what I mean by that, the electrons that you have far away and you pull them all together, let's say each one of them has energy infinity. Who cares? Because what you care about in the lab is bringing them to a small space, and then you care about the energy difference and not the fact that one of them, the self-energy, so to say, is infinity. It's not playing any role. It's also not playing any role because you cannot use it to create bombs and things like that. Yeah, I think this is clear. So the self-energy is important as some concept, but it's not important in a real laboratory unless you can release some part of this energy. Or you want to say it in a different way, when God created this world, he had enough energy to put infinite energy inside these small particles, but from then onwards, we don't care about this infinity because we care about energy differences. So don't be fooled by this infinity. It's not the end of the world. It's not that something really bad is going on, but it is something that you should be slightly careful when you use the formula. If you just use it blindly, you can get infinities, and then you can get all confused. This is why this formula is actually working in practice for continuous row of R. So when you have a continuous distribution row of R, not a discrete, not point particles, the formula that I gave here, like E squared integration, will work perfectly well with no problem. And it will not give you any divergence. It's only when you go to these point particles that you have a problem. Okay, so now we understand this energy. Let us make one more analogy of this infinity that maybe some of you are worried. So the energy, let's say in classical mechanics, is mc squared plus mv squared over 2. Of course, there are more corrections due to relativity that Nadav would kindly agree to teach last week when I was not here. So let us look at this term. Imagine that the speed of light in classical mechanics, let's take it to infinity. Okay, you have here infinity. Who cares? What you care is about the differences of the kinetic energy, how it transforms to potential energy. As long as you cannot take this to be finite, so before Einstein, people would say, okay, this is actually zero, but it's actually infinite. You don't care because you look at energy differences like in our problem. If the electron would have this size, then this would be the self-energy addition to the usual energy, but it will not play a role in transformations of energy, which is the key issue. So I'm saying this is a bit similar, at least to my mind, to what is happening there, and you can just forget about this, and you can forget about the infinite energies. But again, if you do an integration of a discrete charges, you'll get something which is infinite. Okay, so these are some problems. So now let us use this energy concept to describe briefly conductors. So conductors are special objects and I will we'll finish here. So what I want to give you is the message that the concepts of conductors are related to the concept of energy that I was just taught you, but you also studied conductors in the past, so I will mix these two ideas together. So what you know about conductors, so I'm thinking about some conductor, let's say a sphere for simplicity, and it's a conductor. So what you know is the following. And so you know several things. And one of them is, one second, the field inside the conductor, that's the electric field, is what?
Zero.
Is zero. Now let us reformulate this. I'm not going to prove that the two are equivalent. A conductor distributes its charges such that the energy is minimized. These two, actually, one can prove that they are equivalent by some variational calculation, but I'm not going to show that. And I just want to discuss these two statements that maybe before you came to this class were not equivalent, or why should we think about it, especially in the second way. So why is the field inside the conductor zero? There's a simple kind of reasoning. If you add a field inside the conductor and you add charges there, they would start moving. And then if they move, they are not in electrostatics. And first of all, after they move, they will dissipate. They will collide with many things. So to avoid the currents, you want the field inside here to be zero. That is the general thing that you had, I think, before. A conductor distributes its charges such that the energy is minimized. From physical point of view, before answering why this and this are connected, does this make sense? Why do I want to say this at all? The idea is the following. The conductor wants to reach the minimum of energy of the field that it creates. Like when you go, let's say, in kindergarten, you go on a swing and you move, and then you go to the lowest energy because you dissipate. So you lose energy, and eventually you sit down in a chair and you're not moving. You reach the minimum of some potential due to dissipation. What is the dissipation here? The dissipation here are currents that would be created. So let's say I start with this charge and it's not in equilibrium. It will, at the beginning, there will be some charge given some initial. There will be some current for some time, but then you will lose energy. You lose energy as long as you have current because of collisions, because of Ohm's law. And eventually you will have no current because you reach equilibrium, because you lose your energy to heat that is dissipated. So these two things seem somehow related, or it's logical to define it like this. But let us try and understand roughly why the second one is similar. At least we do this for a sphere. So now we can understand this. So imagine we have a sphere, and imagine with the charges are all over the place. So this is, let's say, some charges are inside. This is not a conductor, right? Because what does a conductor do? Where are the charges of a conductor? They are on the surface. Then I have another sphere, and I'm going to use here also symmetry, that the charges are on the surface. And for simplicity, let us assume uniformly distributed, also here uniformly distributed or radially distributed. That's not so important. Now I ask you guys, which energy or which system is higher and which one is lower?
Higher is the charge outside because the charges are closer to each other.
That's a perfect way of putting this. So this guy, the W of E, is bigger than this W of E, the energy here. Only because the charges are close by, but we can also formulate this in a very different way. What are the, more mathematically and a little bit more rigorously, we have here a field outside. And we have here a field out. Let's call this one 1 and this one 2. We have a field here in 2, and we have a field inside here, which is 1. What is the field inside in this case?
0.
It's 0. What is the field inside here? It's something, but it's not necessarily 0. What is, however, E out? E out.
Roughly the same.
Not roughly, they are the same. That's not the point if you have symmetry, because outside it's as if the charges are in this point or in this point. So E out is E equal E out to 1 out. Now, how do we calculate these two objects, these two energies of these two systems? We do integration over all space. So the integration outside here will give you some number. It will give you the same number here.
But it is E1 also.
But the integration over here will give you something. What will it give you? That depends on what is the charge distribution inside. So it can give you different things. But it's obviously that integration for R bigger than R is the same in both cases. And another small point is that when you are integrating E absolute value to the power 2, it's positive number always. It cannot be negative. So so E in, if this was 1, W E in is bigger than 0. And that's why the second guy is winning. So one way to say that there is no electric field inside here is which is what you know already, or is the saying that the conductor reaches some energy minimum, and the energy minimum is related to the field all over the space. That's the idea. This is not a complete proof, but you can prove it with variation principle. I'm not going to do that. It's a functional variational principle. You can use ChatGPT to prove this. Yes.
Because you have a huge number of particles, don't you need to show that the entropy goes to maximum as well?
Okay, I'm not talking here at all about. That's a good question. I'm not talking here at all about thermodynamics or statistical physics. So I'm talking about mechanical equilibrium, where there's no temperature. So when you go in the kindergarten, you swing the swing, you go to the minimum of energy. You don't. The child in the kindergarten doesn't ask, what about entropy? The reason is that it is a mechanical problem of reaching. The temperature is not relevant. But in principle, you are right. What will happen for a small system at high temperature? What minimum do you need? Is it the energy minimum or the free energy, etc.? But here we're talking about zero temperature things. Yeah, but it's a good comment. So okay, so we can now use these two ways of thinking at least, and now we can briefly summarize. Only summarize. This is all given in Griffiths. Some general statements about conductors that follow from these two rules, which are equivalent. First of all, dE inside is equal rho over epsilon 0, but E is equal 0, so rho is equal 0. What does this mean? All the charges are on the surface. All charges are on the surface. We can also say on the surface we have equipotentials. Why is that? If it will not be equal potential, then you'll have some gradient, and then you'll have an electric field, and then you have charges on the surface. And if you have an electric field and you have their charges, what will happen? They all start moving, and this is impossible. So on the surface, we have an sum of a conductor. All this surface has the same value of potential everywhere. Now, we can ask ourselves, let's say another thing, which will be in the, the TAs will also explain this, I hope. Let's say we have a surface. This is a surface enclosing somebody in 3 dimensions. We have here some dA, so outside the field is always normal to the surface. Why is that correct? First of all, what is it in the plane? It's 0, because otherwise you'll fall. And then obviously you have charges here on the surface. So there's no vertical in the plane electric fields because we don't allow currents. So it has to be normal. That's the simple answer. But what happens here? What does it mean if you are normal to the surface? You are creating a jump, because inside the field was 0. So inside 0, inside is 0. So on the surface, we have a jump. Jump in what? In the value of the electric field. If you go a little bit inside, it will not be the same as a little bit outside. Why is that so? Because here there is some charge density, that's all. What is the charge density? This is the sigma. The sigma can change at different locations. But when I look very close to this, what is the sigma? It's created, this is a complicated object, but very close, this is a plane. Looks like a plane at least. So only this sigma locally will determine what is the electric field very close to the field. For example, I'm on this planet, but if I look here, I see something straight. So that means we are living on a straight surface, and there's some elephants underneath us holding all this world. So it's a good approximation. And you can do this trick. How do you do this more rigorously? You create here a Gauss surface, and you say the Q enclosed is given by the sigma times the size of the surface, and this should give you the fluxes from below and above. This is all in Griffiths, and the end result is the following, that this is the electric field. It's given by sigma epsilon 0 n. And this is, again, this is charge per unit surface, so it has units of charge divided by meter squared, which is, of course, the units of an electric field.
Just the Gauss law specific
Location.
Yes.
Read about this in Griffiths if you don't remember. And similarly, it's the same thing essentially. So there are problems that we look at the electric field jump. So yeah, if you want, you can add here for some R, some specific R. So this is the same thing. the minus comes, instead of energy, I want to, electric field, I want to use a potential. This is given by dV over dN. And why do I give you two formalisms? Because, as I mentioned at the beginning, sometimes you solve Poisson equation, and then you need this boundary condition, because you're looking at V, and sometimes you're using Gauss law or some other law, then you're using the E, so you need to know these two boundary conditions. This, what I try to do here is just show very briefly that it is related to this energy concept. So with this, what did we do? We summarized, one second, Griffiths, chapter 2. Chapter 1, it's Griffiths mathematics. You know already. What do you need to do now? If you didn't read chapter 2, then read at least part of it, some exercises. I really recommend that you read this book. I think he's a terrific teacher, Mr. Griffiths. And he's preparing you to some storm that will come in another 5 or 6 weeks. So his notation is useful when you go to the relativistic thing. And he's building up the story slowly, I think. But I think it's worthwhile with many small points. For example, this divergence of energy going beyond what I think you know. What will we do in the next week? We're going to do chapter 3. Chapter 3 will be solutions of Poisson equations. So you had it in some courses, that's true. But I think we can maybe give you some new insights and also improve your technique in solving things. The course is, the grade is 85%, that's the exam. And 15%, that's the exercise. And I truly encourage you to come to the class. I don't mind if individuals have some events, but what I saw in last semester, I never experienced this in my life, that towards the end, maybe it's because I'm getting old, all the students running away. But I think it's more related to the fact that it's easier to watch the movies on YouTube, but it eventually hurts you guys, in my opinion, because you don't form collaborations. We don't talk about things after the lesson. I don't know. Maybe I'm wrong. I know that in Tel Aviv University, they don't allow this beautiful technology to appear. So there are more students coming to the class. So I come from Tel Aviv. Maybe they are right. Maybe we should not allow it on the YouTube or whatever it is. But this is just some thoughts. Okay, so there was a question, and then we can go.
What you writing here? No, the second, dou V over the what?
N. So N is a normal.
Ah.
Sorry, yeah, thank you for asking.
Direction derivative?
It's a direction you take. What is a derivative? You take 2 points and you take the difference between them, and you subtract and you take the difference. But when you are in this point, you can do it in that direction, that direction, that direction, okay. And you need to do it in that direction, which is normal to the.
Okay.
This is the definition of this normal to the surface. So, for example, if you have a sphere, it's radius r. Okay, guys, goodbye.
I have a question. So if you comparing the conductor, if you had a shape like that was like you would have 2 normals, one in front of the other. Like for the left, there would be 2 in front of the other. It would make them go apart.
Slowly. The normal I was talking about here, I'm not sure this is your question. It's close to the surface, right?
Yeah.
So you have 2